Let's finish this part. So last time we were talking about the gas turbines, okay, and how you can calculate the compression, the expansion, and we finished here by saying that the Q generated in the heat exchange, sorry, in the combustion chamber was calculated by a simple equation, right? This, yeah, we finish here. This one, the Q in the combustor was simply Q added is m dot CB delta T. See, just like our swimming pool, huh? Q added is m dot CB delta T. All right, and so here, but here I have to make CP that is really appropriate for the CP that's appropriate for the combustion chamber, right? Something between all air and all exhaust. Okay. And so this Q added is coming from what? From burning the fuel. So m dot fuel times the heating value of the fuel. Okay, and the same equation, if you just bring m dot air over here, you get m dot fuel over m dot air, the fuel to air ratio. And that number is small. That number is like 3% only, or 4%. So you don't really burn that much fuel compared to the air. The majority is air. Okay, you look at the heating value, it's in the 40 megajoule per kilogram. Okay, 40 megajoule per kilogram. Okay, so we know the heat rate. One guy sent me an email. I think he was asking why we have 3412 in the heat rate equation. Why the heat rate equation is 3,412 over the efficiency of the cycle. It's the eta cycle multiplied by eta electric, in case you are generating electric power too. The eta over all. So why the heat rate is 3,412 over eta thermal? So think of the heat rate as 1 over the efficiency. What's the efficiency? Work net over Q added. So what the heat rate is Q added per work net. Huh? He simply, they care about this number because it's the heat rate is how much do they pay divided by what they sell. They pay for the natural gas and they sell the electricity. So they look at Q added divided by the work. And when we calculate the efficiency, which is work over Q, we want this number to go up. But when they calculate the Q added over the work, they actually want this number to be small. When this number increases, they don't get excited. They get super sad when this number go up. They don't want to pay a lot of natural gas, right? So now, why 3,412? Because 1 kilowatt hour is 3,412 BTU. So the efficiency is dimensionless, but the heat rate, rather than saying this much BTU per this much BTU, or here is the heat rate, this is how many joule of natural gas divided by how many joule of work, they can do that. But they rather have it in those units, BTU per kilowatt hour. Why? Because in America, we pay natural gas in BTU. That's the bill. The bill comes in BTU. You use this much BTU this month. Okay? Actually, they also do it in CERM. CERM, which is like what, 1,000 or 100 BTU? What was it? Was it CERM? Huh? 100,000? Yeah. So anyway, the unit is BTU. And so we need to do that conversion, all right? So if you just Google what is convert BTU to kilowatt hour, convert kilowatt hour to BTU, surprise, 3,412. 1 kilowatt hour is 3,412 BTU. Okay, that is the secret. Make sense? Okay, good. So whenever someone asks you for the heat rate, it's simply calculate the efficiency and say the heat rate is 3,412 divided by the efficiency. And it should be overall efficiency because it's also involved the electric generator efficiency into it. Okay, so the ideal cycle was isentropic, constant pressure, isentropic, constant pressure, tuck, 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 tuck. That's Brayton cycle. But the real cycle will have what? Will have not isentropic compression, but you go this way, with the isentropic efficiency of the compressor. And the same thing for the turbine. Turbine does not drop isentropically. It drop like this. There is 4S and there's 4. And in the final, probably I'll give you a Brayton cycle, and then I will ask you to calculate, say, the heat rate. So it would involve calculating this work in the Q, and then be able to calculate the efficiency, just like what he's doing over here. Okay. So now what is that? He is saying that there is also, what's going on? What's going on? There is pressure drop in the combustor. He's saying that the pressure that you go into the combustion chamber with is not the pressure that you would leave. Why? Because that combustion chamber is a bunch of holes that you have to go through, right? It's like really pressure trap, like you really lose a lot of pressure into it. So if I can show you some of the combustion chamber. Here, this is the combustion chamber. So the fuel come here and the air come around it, right? The combustion chamber is sitting here between the compressor and the turbine. Okay, this is for a jet engine, but it's similar for a stationary gas turbine on the ground generating power. Same thing. Bunch of cans connecting the compressor to the turbine. The only difference is that in those jet engine, the shaft is connected to, say, a propeller or a fan. See all this? This is what? This is a compressor, this is a combustion chamber, and this is a turbine. And then the extra work, the turbine drives the compressor, and it has extra work. Where does the extra work go? What is that? What do you think this is? Excellent. Gearbox. Gearbox, so that, say, that propeller run at the right speed for the propeller of the aircraft carrier, or the propeller of the boat, or the propeller of the helicopter, right? Or the gearbox that connect you to the generator. So you need a gearbox and then your shaft. So that's a turbo shaft. Okay. Very good. So point is, a lot of pressure drop through the combustion chamber. And look at how much air goes through the combustion, only 12%, but the rest of the air go around to cool it. So that's why the air-to-fuel ratio is, the air-to-fuel mass ratio is really high. Okay. Here is a smaller turbine, sorry, a smaller combustion chamber where they put the fuel and a lot of cooling, and then everything eventually leaves to the turbine. This is how combustion chamber would look like. Bunch of cans around. But then there is an even better design where the flow is in an annulus rather than cans. Like this. Look at this. Rather than a bunch of cans, there is big annulus that's like basically separate or like the combustion happen all over. But although this is more efficient, they don't like it because of maintenance course, right. If something bad happened here, you have to replace the whole thing, and the whole thing is out of order. But if it's a bunch of cans, and one of them went wrong, you buy the can and you put it in. You don't replace the whole thing, and it's super quickly to change it, right? So that's why they like the can more than the annulus, right? Okay, so that's the fuel part. So most of the time you inject hydrocarbon fuel. So this hydrocarbon fuel are liquid. You need to atomize them. You need to make them droplets before you burn them. Okay, so this is the ideal cycle, right? And this is the actual cycle when you go like this and like this, and there is also a pressure drop in the process. Okay, and we saw how the efficiency is function of the efficiency of a Brayton cycle is function of the pressure ratio, the B over P, the pressure of the combustion chamber over B ambient. Right? The higher the pressure, the better the efficiency. Okay. Very good. So in our book, he then give us a here's a table of different combustion chamber, and you can see the heat rate can sometimes go to 8,000. That's pretty neat. We said like 10,000 is the threshold between like good and bad, kind of. Like you are less than 10,000, you're okay. Above 10,000, that is horrible power plant because the efficiency will be low. I mean, you can calculate the efficiency when you hit 10,000. What is it? If the heat rate is 10,000, how do I calculate the efficiency? That's 3,412 divided by the heat rate would be the efficiency. Right? So what is 3,000 divided by 10,000? Yeah, that's horrible power plant. Right? So I would say like maybe 40% efficiency is borderline acceptable, because a good power plant like the one in Oasu is 65%. So when your efficiency drops to 40%, I mean, that is, now we are not really competitive anymore. Okay, so here's how they can make the gas turbine like really competitive. What they can do to make it go up to a good efficiency. They can do this. This is called regeneration. What is happening over here? They realize that the exhaust of the gas turbine is way hotter than most of the time, it's way hotter than what is going into the combustion chamber. So why are we throwing that hot air, hot exhaust, and spending money heating our air going into the combustion chamber? Why? Well, let's actually get some of this heat into the incoming air. But when you do this, that means equipment, that means cost. You have to build that heat exchanger, right? So its initial cost, again, is running cost. Rather than keep burning fuel all over the life, if you already have something like this, that will save you in the long term. Okay. So in the cycle, right, in a cycle like this, that's what regeneration is. Look at that. Look at this temperature 9 and 3. If 9 is hotter than 3, then it will be a crime to throw this 9 and heat the 3 all the way up to 9 using our own fuel. So what do they do? Before you send it out, you put it into a regenerator. Okay? This is specifically important if this was a closed cycle. If that cycle is running helium, for example, and that heating is not happening because we are burning fuel, but because we are cooling a nuclear reactor. So then this is like, you don't have an excuse. Like, why would you? I mean, I would understand if you're throwing the hot gases out and say, well, it's like repolluted water, air, and we don't want to have problem in our heat exchanger, it will get blocked. But if it's the same fluid or same helium going through the cycle, of course you have to do this. Right? So regeneration is one. The second thing that they do is intercooling. Okay? So what's intercooling? Rather than taking the compressor one shot, they cool the air in the middle. A lot of big compressors have multi-stage with intercooler between them. Okay? And I don't have a good picture for it over here, but I mean, if we Google intercooler, if we Google compressor with intercooler, look at the drawing, I think something like this. You can see how he is actually, when he finished the first stage, he go to intercooler before he go to the second stage. Okay, so that again costs money, right? Because you have to build something like this. Look at this. Compressor, intercooler, then another compressor. And that intercooler sometimes is like really big. And it takes a lot of area for it to happen. But what is the benefit of those intercoolers? What's the benefit of this intercooler? So on the TS diagram, you're supposed to go like this, from 1 till 2, right? This is 2S, and the real one would actually be even a little bit hotter. You would be like this, right? So they are saying that if you just heat yourself up till here, like, sorry, compress up till here, and then take this guy and cool it, and ideally how cool it will get, should cool all the way up to 1. Ideally, T ambient. If I have big heat exchanger and I spend the time cooling, I will go back to 1. And then from this, I will go up here. Let's call this 3S. And then you will come here 3. So this and this, leave it or not, is smaller than that. So the 2 compression is smaller than 1 big compression. So if you want to make this, if you saw this intercooler at your work and you got super impressed, say, wow, that's really cool, but I can make it even better. What would you do to make it even better? I can't hear. With a fan, well, the heat exchanger is supposed to be have enough air cooling from outside, whether with a fan or with a lot of fans or like just big area. He will do a good job and get cool. But how do you make this process even better? Help for a free homework problem. How we can make it even more, like we want to make a compressor that will beat all the compressor in the world. What do we do? More stages. More stages, right? How many? Like how many? 4? No, that some come already made 4. I want to make it even better. What should I do?
Make it 8.
There are another coming already made 8. I want to make more.
Infinite?
Yeah, infinite. Infinite will make us win. How do we make it infinite? So infinite, how we go infinite, by the way? So this is 1 stage, right? Infinite will take me where? This is the TS diagram. Infinite will take me.
Would it take you to 0?
will take me here. No, it will take me to the left. Okay? So infinite, it means that it's constant temperature. That's called isothermal compression. Amazingly, isothermal compression is more efficient than isentropic compression. I know that we always think isentropic is the best, but no, isothermal compression is more efficient than isentropic compression. Now, how do you make it isothermal compression? How do you put infinite number of stages? One company made this, they got a patent for it, and then they really wanted compression to be very efficient. Why? Because they wanted to store energy rather than in battery, extra energy, they wanted to store energy in compressed air. And so they said the only way we can compete with battery is that if our compression process is very efficient, the best efficient compression process ever. And they decided we're gonna make it isothermal. So how do you compress the air isothermally? Say that again. So, but the compression itself is not isothermal if you put it in vacuum. You are also thinking, I want it to be adiabatic, like perfect adiabatic. Isothermal is not really adiabatic. You have to do it really slow, really, really slow, so that the heat transfer have a chance to cool you, right? But they didn't go that route. So isothermal does not mean adiabatic. Isothermal does not mean perfect, perfect insulation. It's the opposite. You want all the heating to leave. So in an isothermal process, by the way, the work equal to the Q. The work that you spend is equal to the Q. That's why the temperature does not increase. Whatever compression you put is equal to the heat transfer that leaves the compressor. Okay. So this company, they once they had this patent, they got like, I forgot how many million of dollars out of investors, and they actually built a power storage plant for the Department of Energy that store energy using isothermal compression. So I want you to think about how do they do it isothermal. I mean, you can go really slow, but that doesn't really help that much. It's not practical. Instead, what did they do? Search for it and find the company. Okay, now I think it's, what time is it? Yeah, you should have told me to shut up 3 minutes ago. So let's take a break until 9, and the exam should be available at 9 o'clock. It's posted under homework. Okay, so let's take a break, guys.